corresponding the corresponding vector to which the forms are dual. We've done this in different notation, but we've done this. So that's omega 1, 3, that's omega 2, 3. Wedge them. What happens? When you take the wedge product of this and that, you get 4 potential terms, 2 of which are 0 because theta 1 wedge theta 1 is 0, theta 2 wedge theta 2 is 0. And so when you calculate, you get 2 terms that survive, namely omega 1, 3 times omega 2, 3 minus omega 2, 3 times omega 1, 3. And what pops out? This theta 1 wedge theta 2 and this formula right here. So I won't write it out, but like it's pretty apparent. If you just take the wedge product of these 2 purple equations, tilt your head, squint, you'll see that. And likewise, straightforward calculation for the other one as well. All right, straightforward calculation for the other one as well. And so then what? Well, corollary. Ooh, this is big corollary right here. This is big and corollary. All caps. I'll allow it. D omega 1, 2 is equal to minus the curvature times theta 1 wedge theta 2. This right here is huge. The proof is just by Gauss's equation. See, d omega 1, 2 is equal to omega 1, 3 wedge omega 3, 2, right? But hey, we just learned that that's notice that the 2, 3 and the 3, 2 are juxtaposed, so that's where the minus comes from. So we get minus k theta 1 wedge theta 2. Awesome. Just awesome, by the way. And so in view of that, we can calculate the Gaussian curvature of the sphere over here. If we got our omega 1, 2, what was it? Cosine phi d theta, right? Calculate the exterior derivative of that. We've almost calculated the Gaussian curvature. Almost. So do it. D omega 1, 2 minus sine phi d phi wedge d theta. But maybe it would be profitable for us to say d phi is equal to 1 over r theta 1, and d theta is actually 1 over r sine phi theta 2, right? So this is minus sine phi times d theta, which is 1 over r theta 1, wedged with theta 2 divided by r sine phi. The sine phi's, they be canceling. And we get minus 1 over r squared theta 1 wedge theta 2. Therefore, the Gaussian curvature for a sphere is 1 over r squared. It's the coolest thing I've said all week. Although I think, oh, did you turn the camera? Oh, okay. I must have done it, I missed it. All right, so now that we got that, let me get out Z projector. Because the next part is very, like this part I wanted to actually calculate with you because I wanted you to see that we can actually go through these calculations. And this is a method of calculation to work out like connection coefficients. We can use the wedge product in this kind of like sneaky sideways stuff. This is the kind of calculations that you need to do for that like Cartan lemma problem, right? No? My point is, calculations with wedge products involve a lot of process of elimination. Sometimes it's like roundabout, how you find out things are equal to other things. Like it's like that. So the thing I'm about to show you guys is lecture 20, lecture 20. And a lot of this I think we've kind of done before, but more in like the abstract. We did some of these things for curves. So, yeah, maybe not show the grade book, that would be good. That was close. I hate editing, you know.
Well, it's not even showing up there anyway.
Yeah, I know. I have learned to hold off.
For this class?
Just generally speaking.
No, the grade book.
Oh no, it was, I don't know what it was for. Let's see here. So I'm looking at my old lecture 20, if I can find it. So this is really the pinnacle, in my view, of the differential geometry. Well, so I don't know, there's two kind of high points. This is one of them, and the other is the Gauss-Bonnet theorem, which comes at the very end, which that's my next thing on our bucket list in here, just to try to understand that. So, so here, basically, this isn't quite right either. I think that it says injective, but I really mean bijective, because I'm assuming, if you read this paragraph, I'm saying onto. I'm assuming onto. So it's an isometry of surfaces if it's a bijection for which the dot product of the push forwards is the dot product of the vectors that were pushed forward. So in other words, it's an isometry if it preserves the dot product under push forward. All right, so this is a little bit different than what we talked about for isometries in 3 dimensions, because there we were actually talking about distance between points and like a function mapping R3 to R3 and maintaining the distance between points. It's a little bit different concept here. Anyway, so the first theorem is that isometries preserve the distance between points, because we define the distance between points by integrating the length of the velocity vector, but the length of the velocity vector is based on the square root of the dot product of the velocity with itself. Everywhere I'm saying dot product, you could replace it with the metric. Like this can all be elevated to a discussion about a surface with a metric, which is the next, that's not this lecture, it's like the lecture after. All of this is still about all of this is still anchored to a surface in 3 dimensions. All right, but not exactly. All right, anyway, so the proof that the concept of length between points is preserved under a isometry of surfaces. So I say an isometry can be thought of as bending surfaces in such a way that the distance on M is maintained, and the preservation of the dot product also preserves angles. So it's a little bit more than just distance, it's also angles. But what we're really after, and we talked about this already in Lee's book, right? A local diffeomorphism versus a global diffeomorphism. This is a little bit more than that, because here, but we also talked about a local isometry in chapter 12, remember? So this is a bit of a review, but this is specialized. We're specializing just to surfaces in R3 right now, okay? Well, I guess not really. I mean, M and N could be surfaces in some other higher dimensional space just as well, all right? What I'm about to argue is that the things I've just covered up with the projector can be done on a surface, a 2-dimensional surface, whether or not it's in R3. It doesn't really matter. So let's get to it. But a local isometry preserves the dot product, but it's not necessarily a global bijection. All right, so like, great. This is very cool. Maybe next class, I got to look at the flow of things, but I might come back and work this out by hand, because this is actually, I think I have a homework problem on this. So here's the deal. If you have a mapping from M to N, smooth surface map, and there's a patch on M, you can basically build, well, you can look at X bar, which is essentially, I don't want to, maybe it's the push, either the push forward or the pull back, however you want to look at it. It's essentially the F-related patch on N. All right, it's the corresponding patch through the mapping F. Then F is a local isometry if and only if for each patch X we have that the warping functions, the E, F, and G, are matching for X and X bar. And the proof is quite beautiful. So it's a local isometry if it preserves the dot product, but this is equal to that, that's equal to that, that's equal to that. But what is that? That's the warping function in the push forward, and this is the warping function on the other side. So they're equal. If there is a local isometry, we preserve the warping functions in this natural way. And you can basically use this to build, you can kind of work this backwards. You can essentially define F by making this happen. Let me show you an example. So here's an explicit calculation of it. I can't remember, guys, if I kept this. Well, Preston, did you get to such a homework problem yet? Maybe not. Maybe I threw this one out. Maybe I had the good sense to throw this one out. But there is a calculation that you can learn here. So like the plane, of course the plane is, oops, well this is dumb. Well, folks at home, so we can get what you pay for, I guess.
It's on my website.
It's on my website, that's right. Lecture 20, Elementary Differential Geometry. So sorry, folks. Anyway, we haven't said much yet. Basically, I just said that local isometry is one that preserves dot products of through the push forward. So we have a plane. The plane has patch UV0, and the cylinder, of course we can patch the cylinder like so, right? And of course XU is U1, XV is U1, and the warping functions for the plane are 1, 0, and 1. For the cylinder, on the other hand, we have also 1, 0, 1. Look, same warping functions, different surface, right? The plane and the cylinder have the same warping functions. So how do you find a mapping from the plane to the cylinder? The argument is that you can define it like this. So F of the plane, that's X of the plane, right? X of UV is that. Excuse me. And then here's your cylinder patch, and so that actually defines a map that maps from the plane to the cylinder. All right, I'm majoring in the minors here. Here's a more complicated version of this. Here's how you can actually find the mapping from the helicoid to the catenoid I showed you guys the other day. The interesting thing is they have the same warping functions, which shows you, if they have the same warping functions, that means they're locally isometric is what it means. So, is that? Let me not bury the lead here. I know our time is Yep, that is it. You gotta look at the link though. All right, you gotta look at the link.
No. I clicked on one of your links on Sunday, Dr. Cook.
You clicked on one of my links.
I clicked on one of your links on Sunday.
It's safe.
No.
It said final exam answers. Note to self, delete.
Final exam answers, note to self-delete. Yeah, you gotta be wary of those.
Well,
Yeah, those are dangerous.
I don't know why I ever clicked on it.
Yeah, that one I could have told you.
I could have told me.
So, if we have a mapping from one surface to another, all right, an isometric invariant is something that is preserved under an isometry, all right, and so the question is, which of the concepts, like the shape operator, the connection coefficients, the dual frame, the EI, the unit normal, which of these belongs to the geometry of M alone? If it does belong to the geometry of M alone, there should be some sense of preserving it under a local isometry, and if not, well, it's not. So let me show you So the first observation is simply that a connection form, omega 1, 2, equals to minus omega 2, 1, is the only one form that satisfies the exterior derivative of the coframe equals to that and that. Like those two equations uniquely define omega 1, 2. All right? Like if you look at the exterior derivative, in other words, if you calculate the exterior derivatives of the coframe, that uniquely fixes a one form, omega 1, 2, such that it wedge products with theta 2 and theta 1 like this. Here's the proof. There's only one. All right, so that's one thing. Then we must free our mind. We must free our mind of the covariant derivative that we have talked about in the last two lectures or so. And we must define the connection coefficients in view of the previous proposition. We define omega 1, 2 by the exterior derivatives of the coframe. That can be done whether or not your surface is a subset of 3 dimensions or if it's a subset of 20 dimensions. If you got a surface, you got a coframe on the surface, you can calculate exterior derivatives. Although I do suppose you need some notion of, maybe we do need some notion of like perpendicularity. But anyway, so let me not distract myself. So that defines omega 1, 2. All right? And as such, and then we can extend linearly. Like we just extend linearly. So now we've defined the connection coefficient omega 1, 2 without any use of the covariant derivative. The covariant derivative comes with the notion of 3-dimensional Euclidean geometry. It's baked into the cake of the covariant derivative. It's in there. This, not so much. Anyway, so so like I said, omega 1, 2 satisfies the structural equations by lemma 5.1. And if we had an isometry, we can say the push forward of E1 is E1 bar, the push forward of E2 is E2 bar. And if we define omega by the exterior derivative like that, because the push forward plays nicely with the exterior derivative and the wedge product, the push forward of omega, like the push forward, the connection form is going to map to the connection form is what I'm trying to get to. I think I state that more plainly here in the next bit. Yeah, here it is. So if we have an isometry, we have tangent frame field on M, and then we have a push forward to M bar, then number one, well, this is essentially just the push forward of, well, this is pullback. I'm an idiot. Pullback, right? Forms pullback. So the pullback of theta bar 1 is theta 1, and the pullback of the connection coefficient is the connection coefficient. That's very cool. And the proof is the usual pullback calculations. And but what's really, really beautiful is that gives us Gauss's awesome theorem. And Gauss's awesome theorem is simply this, that the Gaussian curvature is an isometric invariant. Explicitly, if we have an isometry from one surface to another, then the Gaussian curvature is equal to the Gaussian curvature of the image surface, where we define the Gaussian curvature to be the coefficient which appears from the exterior derivative of omega 1, 2. Notice that we've defined omega 1, 2 without regard to the covariant derivative in R3. We've done it just with the surface calculus, just with the exterior derivative of theta 1, theta 2. And as such, well, and here's the proof, if we look at this defines that, and then we can pull the exterior derivative, pull back outside the exterior derivative, but then this by definition is minus k theta bar 1, theta bar 2, but on the flip side, I can pull back and so forth, and then I look and compare, and I get that the curvatures are equal. So this is not how Gauss saw it. So this is Gauss's theorem egregium, which literally means my awesome theorem. And basically, and so just to give you a kind of a brief overview exactly what's going on here, the exterior derivative of the 1-2 form gives us, minus the Gaussian curvature times theta 1, which theta 2. That means that k can be calculated without knowledge of the shape operator. But the interesting thing is that k is also the product of the principal curvatures. The principal curvatures are the eigenvalues of the shape operator. So while k is intrinsic, neither k1 nor k2 are. The principal curvatures for the catenoid are not equal to the principal curvatures for the helicoid. Like, those aren't preserved. They're different. They're, anyway, so it's complicated in that sense. So the k1 and k2 are tied to the shape of M as it appears in R3. So while k is intrinsic, neither of the principal curvatures are. Yet, of course, the k1 and k2 taken collectively are related to k bar 1 and k bar 2. Their products are equal, because the Gaussian curvature is the product of the principal curvatures, because the determinant of a 2 by 2 matrix is the product of its eigenvalues. More than this, the term flat is from an intrinsic perspective. So the inhabitants of the cylinder geometry is the same as if they lived on a plane, at least locally. You can walk back to where you started in the cylinder. That's kind of weird. But what does this all mean? This has an application to map making. You've heard the claim before that you cannot make a faithful representation of the globe on a plane, right? In such a way that you preserve distances and angles. If you could, what would that be? That would be a local isometry of the globe onto the piece of paper. But the paper is flat. The curve is not. The sphere is not. The curvature of the sphere, we calculated it today. It's 1 over r squared. This proves it's impossible to make a faithful map for a sphere using paper, flat paper at least. Now, if you could find some spherical paper, you could do a good job there, So,
You prove the Earth is flat.
you prove the Earth is flat. Yeah, well, that's true. If you could make a faithful map for the whole Earth, but, it's an interesting thing. I need to spend more time on this to give such people more serious answers, because some of them do really mean well, and they're trying to interpret Scripture literally. But they also tend to not pay a lot of attention to other literal things, like they seem to always think that the Earth is a disk. What about the 4 corners of the Earth?
4 corners of the disk.
The 4 corners of the disk. Well, I always advocate for a hollow Earth, and I would like to say I was advocating for a hollow Earth. I think I was advocating for a hollow Earth before the recent, big, Godzilla, King Kong stuff.
I was advocating for it in 9th grade.
9th grade?
Yeah.
Like, what kind of, like a cylindrical Earth, or?
A flat, hollow donut Earth.
A flat, hollow donut Earth.
I think I've been advocating for Hollow Earth ever since I watched Bleach.
Is that a part of Bleach? Is it?
They're called hollows.
Oh, hollows. Interesting. Okay, well, anyway, that's so next up is we try to talk about a surface as its own entity, and decouple. So all this classical Gauss stuff is based on the surface being a subset of R3. And you've got all these special formulas that are based on the cross product and the dot product in 3 dimensions, right? So next up, we look at surfaces more as manifold theory, as being geometric objects in their own right that are paired with a Riemannian metric, and what can we say in that context? And that ultimately culminates in the Gauss-Bonnet theorem. But anyway, I think that's it for today, unless you guys got questions.
So the diffeomorphisms are weaker than most other relationships.
Is it
in the sense that
is a diffeomorphism weaker than an isometry? Yeah.
and then
Yeah.
most other.
But a diffeomorphism is stronger than a homeomorphism. Homeomorphism is less structure. Every diffeomorphism is automatically a homeomorphism. But
Two things can be diffeomorphic and not isometric.
that is true. Yeah, isometric is a stronger thing. A little kind of a halfway house is conformal. Conformal is a preservation of angles, but not necessarily distances. But
It's
yeah.
a batch in the sphere is like.
Yeah. And then there's like more interesting like general questions, which is, are there things other than distance that you want to preserve between mappings? Can you look at some like set of spaces that is relatable, like different objects in different spaces in this family of spaces, they're similar according to some other notion, maybe not of distance, but of some other structure. Like, I think this is more or less like the last chapter on contact structures. And there's all kinds of things beyond just Riemannian geometry that we know now. But anyway.